Multivariable Calculus, Section 12.10, Second Derivative Test for a function of two variables. So here we have a little red point shown on this surface where both the partial derivatives are equal to 0. That's called a stationary point. A saddle point is a point that is a stationary point but not a local extremum. The name derives from the fact that the prototypical example shown below is a surface that curves up in one direction and curves down in a different direction, resembling a saddle or a mountain pass. Sliced by one vertical plane, the trace has a maximum. Sliced by another, a different vertical plane, the trace has a minimum. Some sources call this particular configuration a horse saddle point because it looks like the saddle on a horse. Now there are other kinds of saddle points. For a function of one independent variable, a saddle point is a point which is both a stationary point and a point of inflection. It is a point of inflection, not an extremum. This is from Wikipedia, and this is what we call an inflection point, but it's if the tangent line is horizontal through the inflection point, then it's also a stationary point and a saddle point. Now there's a thing called a monkey saddle point. It belongs to the class of saddle points, and its name derives from the observation that a saddle for a monkey requires 3 depressions, 2 for the legs and 1 for the tail. So if you can imagine a monkey sitting astride there with his tail coming out towards you down that sloping portion of the surface, that's a monkey saddle point. Now, according to dictionary.com, a saddle point is a noun in mathematics, and it means a point at which a function of two variables has partial derivatives equal to 0, but at which the function has neither a maximum nor a minimum value. According to Wikipedia, in the most general terms, a saddle point for a smooth function whose graph is a curve, a surface, or a hypersurface is a stationary point such that the curve, surface, etc. in the neighborhood of that point is not entirely on any one side of the tangent space, plane, or line at that point. Now, these two definitions are rather general. Edwards and Penney got a lot more specific. According to page 885 of Edwards and Penney, a saddle point is a point on a surface in 3 space that looks like a local maximum from one direction, but like a local minimum from another direction. Now this is a lot more specific. It has more criteria than just having 0 partial derivatives. So we're going to adhere to Edwards and Penney's definition of a saddle point. You don't really have to worry about it because I'm looking at the odd-numbered problems. There are no discrepancies between the various definitions. But for some of the even-numbered problems, I found that Edwards and Penney did stick to their own particular definition. And so partial derivatives equal to 0 can mean minimum or maximum or saddle point, or in the case of Edwards and Penney, neither of those 3 things. None of those 3 things. Extrema maintain their minimum or maximum status regardless of the vertical slicing. So there's a minimum and there's a maximum, and no matter how you slice them vertically, every trace will have the same minimum and maximum point. Critical points. Given z equals a function in two variables, a necessary but not sufficient condition for extrema is that both partial derivatives at the given point are 0, or that one or both are undefined. Now in the textbook examples, we rarely find a function that has an undefined partial derivative, but it bears mentioning. Now according to Edwards and Penney, critical points where all of the partial derivatives are equal to 0 can be extrema saddle points or neither. Well, I was a little confused about neither, and I wondered what that might look like, so I came up with some examples. Here's a surface where the trace on any vertical plane containing the critical point, shown in black there, always looks like a cubic, which has neither a minimum nor a maximum at that critical point. So you wouldn't be able to slice it and get a minimum or a maximum. A little bit hard to picture, and my drawing isn't very good, but basically, no matter how you slice it, you get a cubic. So you can't, according to Edwards and Penney, that is not a saddle point. And I think I side with them because I can't imagine sitting on a point like that. And here's another example that might be appropriate. Imagine a point right there where maybe if it flattens out just at that one point, you could have tangent lines in parallel to the x and y axis with a slope of 0, and so the partial derivatives would be 0, but you can't slice it and get a minimum or a maximum. And so according to Edwards and Penney, that is not a saddle point, and I agree with them. Second derivative test for a function of two variables. Define the following. A is second order derivative, B is a second order derivative, and C is a second order derivative as shown at a particular point. And then triangle at that particular point is the product of A and C minus B squared. The second derivative test for a function of two variables says, let this function have continuous first and second order partial derivatives in some neighborhood of a critical point AB. If A is greater than 0 and triangle is greater than 0, then you have a minimum. If A is less than 0 and triangle is greater than 0, then you have a maximum. If the triangle value is less than 0, then you have a saddle point. And if the triangle value equals 0, then this test fails to determine the nature of this critical point. So it's similar to the second derivative test in single variable calculus, but a little bit more complex. Now, the proof of all this is in your text, should you care to read it. Number 2, classify all the critical points of the given function of two variables. So we need the partial derivatives with respect to x and y, and then we need to find their zeros. And this particular function only gives us one possible critical point. So then we need the second order partial derivatives, and so they end up just being the coefficients of x and y. And then notice that b is 0 because there is no y term in the partial derivative with respect to x. And so the partial derivative, the second order partial derivative of the partial derivative with respect to x with respect to y then is 0. So then we multiply a times c and subtract b squared to get the triangle value, which is positive. And so we have a positive triangle and a negative a value, which means we have a maximum. So we plug those values into the original function and we get 40. And so the absolute maximum is 40. Since there only is one possibility, it has to be absolute. Now, checking your handy-dandy quadratic surface card, you should reveal to you that this surface is in fact an elliptical paraboloid. And it does have a max because it's upside down. Number 16, classify all the critical points of the given function. Function of two variables again. So again, we need the partial derivatives with respect to x and y. And this time when we set them equal to 0, we can solve for x in both cases. And so since it has to be the same point for both, we can set those values, those quantities equal, and then solve for y. And we get two values for y, which means we're going to have two values for x. So I'm going to plug those values for y into the easiest equation for x, and I get x is -1 when y is 1 and -5 when y is 3. So we have two possibilities, and we need the second order partial derivatives. And depending on which set of points you plug in, you get the same value for A and B, but you get two different values for C. So for the first point, negative 1, 1, triangle comes out negative, and for the second point, negative 5, 3, triangle comes out positive. Therefore, when triangle is negative, it's a saddle point, and when triangle is positive, then we have to look to the A value, and the A value is positive, and so that would be a minimum. So when we plug in negative 1, 1, we get 1. And when we plug in negative 5, 3 into the original function, that is, we get negative 3. There is a saddle point at negative 1, 1, 1, and a minimum value of negative 3 at the xy point of negative 5, 3. And so it's just a matter of keeping straight your different values and being careful with your computations. Number 22, classify all the critical points of the given function f of xy equals this quantity. Now, I chose this one because it's much more complicated during the computations, but the idea is all the same. So we need the partial derivative with respect to x using the product rule, and then we can factor some things out, and it's clear that this will only be 0 if x is equal to 0. Then we need the partial derivative with respect to y, and again we're using the product rule and the chain rule actually. And then factoring something out, it's clear that this will be 0 when y is 0, or since x has to be 0, we also get that last factor equal to 0, plugging in 0 for x, and that gives us two solutions for y, plus or minus 1. So actually we have three solutions for y, 0, plus or minus 1, but x always has to be 0. So here are our three critical points. Now let's review the triple product rule, because we're going to need that to take the derivative a second time. The derivative of f times g times h is three products added together, each one having the derivative of one of those three functions. So we're going to use that to compute fxx and fxy and fyx. I mean fyy. So a is fxx, and we take the derivative of fx in the original computation. To show that, we've got the derivative of 2x is 2, and the derivative of e to the x squared minus y squared is e to the x squared minus y squared times 2x, and the derivative of that quantity with respect to x is just 2x. Now to get a, we just plug in the values. You don't have to simplify this. And so we get a is 2 at 0, 0, and 4 over e at the other 2 points. So a is always positive. Now we need to clean this up a little bit because I don't have enough room to continue. So now I'm going to compute b, which is fxy. And again, we're going to use the triple product rule, replacing 2x with its derivative with respect to y. That would be 0, and then so on. And then we plug the values in, and we get 0 for every single b value. Now, we need to do c, which is fyy. So I'm taking the derivative of that quantity that I circled there, again using the triple product rule, replacing each of the three factors with its respective derivative with respect to y, and then evaluating at 0, 0 we get 2. Then evaluating at the other 2 points, we get negative 4 over e. So then triangle is a times c minus b squared, which at 0, 0 is positive, and a is also positive for that point, and so when we plug 0, 0 into the original function, we get 0, and that's a minimum value. So then we go back up to our other 2 points, and we have the same a, b, and c values for both of those points. So triangle for both of those points ends up being negative, And also when we plug those 2 points into the function, we get the same z value, namely 1 over e. And so those 2 points are saddle points. Number 24, show that AC minus b squared equals 0 at the origin, and then classify this extrema by visualizing the surface of this function. Okay, so again we need the partial derivative with respect to x and the partial derivative with respect to y, which are 0 only if x and y are 0. So we have shown that this is a critical point. The only critical point, in fact. And so a is 6x, which is going to be 0 at 0, and b is 0 already, and c is 6y, which is also going to be 0 at 0, 0. And triangle is also 0. This means the second derivative test fails to tell us anything about this particular critical point. So now we're supposed to visualize the surface. Well, if x is 0, then you get a cubic in the zy plane. And if y is 0, we get a cubic in the zx plane. So that cubic's coming out towards you. So according to Edwards and Penney, this is it's not a saddle point, nor is it a min or max, obviously. According to some other texts, they might call this a saddle point, but we're going to call it not a saddle point. Therefore, 0, 0, 0 is neither an extreme point nor a saddle point, according to Edwards and Penney. Number 26. Find the points on these two skew lines that are closest together. And here's the parametric equations for the first line and parametric equations for the second line. So we're going to let our function be the square of the distance between any 2 points on these two lines instead of the actual distance with the square root, because that makes the computations more difficult. So we'll use the square of the distances. And so we subtract the x values and square them, subtract the y values and square them, and subtract the z values and square that quantity. So now we need the partial derivatives with respect to s and t. Here it is with respect to s, and if we set it equal to 0, we can solve for t in terms of s. Likewise, the partial derivative with respect to t is computed this way using the chain rule. And we can simplify that and again solve for t. So if t is equal to these two quantities, then by the transitive property of equality, we can set those two quantities equal. Solving for s, we get s equals 6/11, and then substituting 6/11 into 5/6 times s, we get 5/11 for t. So now all we have to do is plug t and s into our linear equations to find the 2 points. So the first point on the first line is given by 5/11, 16/11, and 10/11. And then for the second point, we plug s values in, and we get 12/11, -5/11, and 17/11. So these are the 2 points on the 2 lines that are closest together. And now I leave you with an interesting surface. This is a helicoid changing into a catenoid. Enjoy your problems.